Very much for the invitation, and it's a pity not to be in Montreal to attend the meeting. Typically, not being at a live meeting means that all kinds of obligations at home just continue. It's always very hard then to follow all the interesting lectures that are going on. Thanks to the organizers, I'm really happy to be able to, even though it's a holiday today actually here. So just to get the feeling, I went to university. And so I want to explain a little bit about the title. So let me start off with the matrix orthogonal polynomials. Actually, a long time ago, when I was still planning to come, I was talking to Alberto Greenbaum. I think he's around at the moment, but he was supposed to come then as well, and already set up a meeting. So in his honor, I should say that these matrix orthogonal polynomials, that they go back to the work of Carton from the 40s. So it's really very old stuff. He did it in a single variable case, and this is mainly about multivariable. And Carton actually did it in the study of defect indices of differential operators, and later on also he considered the moment problem for this set of polynomials. But now we are more interested in the cases where you can link it to representation theory. And I should mention also that one of the first papers doing this is a paper by Alberto, joined with Ines Paceroni and Alfredo Tirao from like 20 years ago. But I should also say that actually this has already been predated by a paper by Kornwinter from 1985. And so there are actually quite a number of results in this direction. So in a sense that this is even more old-fashioned than Martina's talk, so I'm sorry for that. So it's really old-fashioned. And I'll just want to discuss with you some results that were done by work I did with Maarten van Pruis, who is currently in Nijmegen, and Pablo Roman, who is in Cordoba in Argentina. And also part of some explicit calculations at the end is joined with Jia Liu, who is a PhD student in Nijmegen and close to defending her thesis at the end of. So that part is based on this archive paper. So let me go through this with you, and I hope that it is kind of clear. So I was unfortunately a bit late starting preparing this, so I decided to write the stuff down. So I'm actually going to look into what are commutative triples. So I'm going to define what a commutative triple is. And I will restrict myself to the compact case, meaning that the group G will also be compact. So I'll take any Lie group, let's say Lie group G, although that's not really necessary. I'll take any compact subgroup. And there is one particular favorite irreducible representation of K hat. And any representation in this talk will be a unitary finite dimensional representation. So I will not worry about this. So this star will be some fixed irreducible representation of K. And then it is said that the pair G, K, and tau is a commutative triple if you take any representation of G hat, any irreducible finite dimensional unitary representation, you restrict it to K, then the multiplicity of this fixed representation tau, that should be at most 1. And then it's a commutative triple. So these commutative triples, of course, are well known in case you take, so if you take tau, so the very special case that you take tau a trivial representation, then this is just a Gelfand pair. Oh, I think I have it on the next slide, but this is something you all know very well. And in order to keep track of the representations for which this is actually equal to 1, I introduce this notation. So this is the P plus of G of tau. These are all the irreducible G representations that contain tau exactly once. So these are the representations that contain the fixed K representation tau. So if you would take the trivial representation here, these are the spherical representations. These are the representations of G that have a spherical factor, meaning a K fixed factor. So that is the analog of what is a Gelfand pair, which will be on the next slide. So if you have such a situation, so let's assume that we have such a situation of a commutative triple, then actually, if I take any of these representations that has this fixed k representation tau sitting inside pi restricted to k, and let's say that we use this for the G representation space and this one for the K representation space, then means that I have some J, which is a K intertwiner of the K representation into the G representation. This K intertwiner J will be unique up to a constant, and since we assume everything to be unitary, it will be a phase factor, unique up to a phase factor. So this J essentially is unique up to a phase factor because of the fact that we have only multiplicity 1. Then we can just define a very particular function phi that we think of as a function of depending on pi and the tau that is fixed. And we think of it as a function g that ends in the linear maps from vk tau into itself. And essentially what you do is you go with a j, you start with j, you map vk tau into the representation space of G, and then you act by pi of G, and then you project back again. This is then called a matrix spherical function, and these matrix spherical functions, they are then the object of study, and we would like to be able to understand them in some more detail. So let me also emphasize that because you have J and the adjoint of J, this does not depend on the choice of the phase factor. This will drop out. So this is uniquely determined, and that's because of the fact that we have the multiplicity condition being equal to 1. So these are these matrix spherical functions. And if you think of the case, for instance, that the K representation would be one-dimensional, then essentially what you have here with embedding J and the projection J star, then essentially you would take a suitable matrix entry of pi of G, which would be the corresponding spherical function. Then it's no longer matrix valued, or if you want, a one-by-one matrix valued function. So you can see that the ordinary spherical functions that you're used to for a one-dimensional representation of K, like the trivial one, would give you back the standard way of spherical functions that are established as matrix entries of an irreducible representation of G, where you have a K fixed factor, and then you take the inner product with respect to this K fixed factor. So in a sense, this will generalize typically the stuff that you know about matrix spherical functions, right? So for these compact groups, these spherical functions in the scalar case, they will typically be Jacobi polynomials or subclasses like Gegenbauer polynomials, Legendre polynomials. So you should think of these matrix spherical functions as some kind of analog of these type of functions taking values in the matrix algebra. So this is what is the object of study, and we would like to understand this in some more detail. The first observation that we have here is that we immediately get, because J is a K intertwiner, so is the adjoint of K, is that you can take out the action of K on the left and on the right. So it comes out with the action of the K representation tau on the left and K representation of tau on the right. So it is a function which is the K action on the left and the right is completely determined. So that space of functions that we should give a name, we call it E of tau. So these are all the functions, let's say continuous functions, that have this transformation behavior, that the K1 comes out as a tau K1 and the K2 comes out as a tau K2 on the right-hand side. Okay, and of course here you have to take into account that this is not commutative, so you really have to make sure that these can be, that you put them on the right side of the equation. You can also think of this E tau as some kind of representation space. So if you think back of the trivial case, which is down here, the special case that you take the trivial representation, then the corresponding space is the space of bi k invariant functions, and then you get the classical spherical functions as bi k invariant functions. So here it's not bi k invariant. So bi k invariant you can think of as the polynomials on G, or the functions on G, which are left and right invariant under the left regular representation and the right regular representation. So you can think of them as the k times k invariant functions of the functions on G. And similarly, you can think of this as the if you take the space of, so let me put that here maybe, so you can think of, say, the polynomials. You can think of this as a k times k module. You can also think of, in the obvious way, the representation of times k on this space. And then this, so then this is a k times k representation, this is a k times k representation. And essentially, if you just take the invariance, k times k invariance, then you exactly get this space. So you get a kind of similar interpretation as in the case of the spherical functions for the trivial representation talk. So this is the space that we would like to understand a bit better, and we would like to make explicit in certain special cases, just as you want to establish the spherical functions in terms of explicit functions. Maybe it's good to mention here also that if you that there's a characterization of this commutative triple as in the classical case for the trivial representation. So if you define the convolution product in this way, the convolution of two matrix valued products, matrix valued functions, then you have to take this as a matrix valued function, this one. So you multiply these two and you integrate essentially term y. So you integrate each entry separately. So the outcome will be a matrix, and that will give you a matrix valued function f convolution g. And actually you can easily show that f convolution g does indeed satisfy the same left and right k behavior, and it is contained in this E tau space. So that's not so hard. And then the proposition, the classical proposition is that if you have a commutative triple, then this E tau is commutative as a convolution algebra and vice versa. So you can characterize this in terms of a commutativity of the convolution product. And again, if we go back to the special case that is way more familiar to many people, is so if you take the trivial representation, then this is a commutative triple if and only if this is a Gelfand pair. And then this space corresponding to the trivial representation, these are just the bi k invariant functions. And if you then call the function phi pi, this is this capital phi, but of course now it's 1 by 1 value, so it's a scalar valued function. These are exactly the spherical functions, even the zonal spherical functions. So this is the object of study that we want to get a grip on. What we do is we will go to a compact symmetric pair. I'll assume that G is semi-simple, and you can keep in mind these two kind of cases. So the first one is like how to view the compact group as a symmetric pair, and the other one is also a very classic example of a symmetric pair, even an Hermitian symmetric pair. But we are in this context of semi-simple Lie groups. I will identify the irreducible representations with highest weights and call that P plus of G. So now I think of pi being labeled by a highest weight lambda. So lambda will be highest weight. And similarly for k, tau will also correspond to the highest weight mu. So now I think more of tau as being labeled by mu, which is a highest weight, and pi as being labeled by another highest weight, but then for g. From now on, we will do this. We will assume this. And actually, I want to focus at some point. I will focus on this case in more detail, and I will do that for the case n equals 2. And there are several more results for general n, but let's we do it. So then there are some facts that we can easily establish, or that we can see that they are analogous to the case that you know for spherical functions. Well, first of all, this space, and now I call it also E mu, not E tau anymore. This space is spanned actually by all these phi mu lambdas, where lambda is in P plus G mu. So, of course, what I didn't say anything, so I still assumed it's a commutative triple. So you could wonder, is there any mu that does the trick? And of course, we know that the trivial one does it, because any symmetric pair is a Gelfand pair. So at least we have the trivial representation, but then of course we would get back to the classical situation of spherical functions. But in all these cases mentioned here, there are non-trivial examples. And actually we have to impose more conditions even further on, and they will also satisfy these additional conditions. Okay, so it is spanned by all these functions. So these functions span the space, and this is essentially the Peter-Weil theorem. There is an orthogonality for these functions. If you take lambda and lambda prime to correspond to different representations, then this integral will give you 0. And this is just Schur type orthogonality, and you also have an explicit expression in case lambda prime equals a lambda. Another thing that you could observe here is that if you take the product of phi x and psi x adjoints, then at least that function is a right k invariant function. And if you then take the trace of this, then it's also going to be left k invariant. So that means that this function, if you take any function of this type, then it will be bi k invariant. So it will correspond to E of the trivial representation, where now I label the trivial representation with the highest weight 0. This E mu is an algebra over E naught. If you take this E mu and you multiply by a scalar function, which is bi k invariant, it will satisfy the same left and right k behavior. So it's an algebra over E naught. And as an algebra, this is free, and it's also finitely generated in general. Okay, so we are not going to use this, but but what we would like to understand is what is the structure of E mu in terms of E naught, and I will try to give an explicit answer later on using some additional conditions. The other thing you can also observe, which is more in line with the convolution algebra interpretation, is that if you take any f and you send it to this number, then actually it's a character of this commutative algebra. I will not use this, but that is in the line with characterizing commutative triples as commutative convolution algebras. And then, of course, we also know that the Casimir operator, if we assume we're in a simple case, the Casimir operator acts in a suitable way on such a matrix spherical function, and it will be an eigenfunction with a specific eigenvalue, which is this inner product of lambda with a suitable inner product on the Cartan, and also rho is the half sum of positive roots. So there is some explicit eigenvalue. So this is all stuff that one knows. And we would like to make it more explicit in particular in this case. That is more or less, I hope, clear what we are trying to study. And if we go to the case of these semi-simple compact symmetric pairs, then we have, of course, a lot of additional structure theory available. So we have to use this a bit. The first one is that we have some kind of Carton decomposition. So G is K, A, K. There's some abelian group A that does it. The dimension of A is the rank of the symmetric pair, and the rank will determine the number of variables in the special functions that will pop up. Then we have M as the standard notation for the centralizer of A in K. And then the reduced Weil group is the normalizer of K. Normalizer of A and K modeled out by, not by A, this should be M, sorry for that. So that will be the reduced Weil group. So in the first example, this will be Sn plus 1, and in the second, Sn, and in the second example, it will be the reduced Weil group for type PC. And because of this decomposition, the Cartan decomposition, we also know that if we take such a matrix-valued spherical function, we can restrict it to A. And if we restrict it to A, then we're completely done because of the left and right K behavior. So it suffices to know the restriction to A, and then we know the whole thing. And then this calculation, it says, well, if I multiply by the K representation of highest weight mu, that's this one, I'll take it in an element M. Then by definition, this is from K, so I can move it into the spherical function. So it's the phi mu of lambda of M times A, but M is in the centralizer, so it's the phi mu lambda of A times M. And then I use again the fact that M is in K, so it comes out on the right-hand side. So you get this one on the right-hand side. So if you then look at this, it means that this phi mu lambda of restricted, well, when you restrict it to A, then it has to end up in the M intertwiners of VK mu. So it is it's worthwhile to study the restriction of the highest weight representation of K of highest weight mu to restrict it to M. And then there is a general result that this will also split multiplicity free. So that's a result you can either find in papers from Kobayashi or Dietmar. And it will split multiplicity free, and let's say that the corresponding highest weights of M are these sigma i's, and that we have capital N of them. And the capital N will be the size of the matrix that will pop up at some point. And then, well, then we can just act by W. We get an action on the M types. So they will be permuted by the action of W. And essentially, this function is W equivariant. So essentially, you need to be able to calculate it on, well, if W, for instance, would act like on a single orbit on these ones, then you just have to calculate this one only restricted to one of these modules of, say, the M module restricted to something. There is a lot more structure available, and then we can actually say much more about these functions phi mu of lambda, and we would like to understand them a bit better. And if we restrict to A, then of course we can act by the radial part of the Casimir operator, and since we're in the semi-simple setting, we actually know how to do this. So this has essentially been done by Harishchandra, and the paper by Kasselman and Milicic gives you a way to do the calculation in a very explicit way. And so what we want to do is we want to determine these functions restricted to A, and we want to find all kinds of properties related to the group theory here. The main properties are orthogonality and the fact that they are eigenfunctions to some second order invariant symmetric differential operator that comes from the action of the Casimir operator. Okay, now come the additional assumption. They're slightly more technical. We also know that these assumptions work, but it's also clear that these assumptions are probably not optimal. So let's just go through them. So it was phrased in the paper with Maarten van Pruijsen and Paulo de Man. So the first is that we have some set so that we can have a structure for this set, namely as a direct, that's a unique description as some minimal elements, some from, say, the bottom, plus spherical elements, so the ones that correspond to the trivial representation. So that's an assumption. And we moreover assume that this B mu is in a one-to-one correspondence with all the M types that occur in the K representation of highest weight mu. Let's say that these are sigma 1 up to sigma capital N. Right, so we want this to be into a one-to-one correspondence. And essentially, you can think of these correspondence as a restriction to certain tori of the various subgroups. That is the first assumption, which is also something that you need to check and which is not in general true. Since we are in this semi-simple compact symmetric space case, we exactly know what this is. We know that the spherical representations are labeled by P plus G0, and that is a non-negative linear combination of certain lambda i's, where n is the rank, so the dimension of A, and these lambda i's are the generators for these spherical weights, and they all have been classified in a paper by Kramer back in the 70s. So essentially, we all know this very explicitly. And why is it that you can expect this? Well, this is kind of the reflection of the fact that the E mu is an algebra over E naught. So you can multiply by spherical functions. But if you multiply by spherical functions, if you take two matrix entries from representations and you take the multiplication of this function, then essentially it's a matrix entry from a tensor product representation. So this requirement more or less reflects the fact that you want this to understand this E mu as an algebra over E naught. So as you want to understand the matrix valued spherical functions as an algebra over the by K invariant functions. And then there is a third condition, which is even more technical in a sense. So if I take any lambda in P plus G, so that it reflects a representation, a highest weight representation of G, We put this for the set of weights that occur in the representation Vg lambda. So Vg lambda has a decomposition into weight spaces, and we collect all the weights that occur in this set P plus of G lambda. So that is the set of weights that occur in the highest weight representation. So that is some saturated set, which is bounded by the convex hull of the Weyl group orbit of lambda. So that is something known, and we only need to know this essentially for the representations that correspond to these generators for the spherical weights. So essentially, this is a very limited set. And then the condition says that if I take any nu in this set of bottom elements, right, this generating set, any generator of a spherical weight, and for any weight in the corresponding highest weight representation with this spherical weight lambda I, and then assume that nu plus eta is actually an element of this P plus G mu set, so it contains, so it's a dominant highest weight, and a corresponding representation restricted to K contains tau. Then according to the previous condition, I can write nu plus eta as nu prime plus lambda, where the nu prime is again such a bottom element, and this lambda is a spherical element. So this lambda is a spherical element, so I must be able to write it as a linear combination of the generators of these spherical representations of the spherical highest weights. And I write it like this, and then the constraint is that this sum is at most 1. So most elements are 0, and at most one of them is 1. That is essentially what is this condition. So this condition is a kind of technical, and it's a bit more difficult to verify, and we also know that there are interesting cases where this condition is not satisfied. Okay, and then the notation is that the length of lambda is this set, the sum of these coefficients. So these are the additional assumptions. So the first assumption essentially is related to the fact that you want to understand E mu as an algebra over E0. And the second condition essentially has to say something about that you can multiply by spherical weights, but you don't want the degree to increase too much. So somehow this is a kind of constraint on a certain degree. And if you assume these conditions, so these additional assumptions, then actually you can prove the following. Oh yeah, so let me introduce phi I for the functions that correspond to the zonal spherical functions that correspond to the lambda i's. So essentially in the previous notation, it would be the phi of the, where the K representation is the trivial one, and then you take any of these generators. Then we know that these phi i's, these are generators of the continuous bi-K invariant functions, and essentially we know that the bi-K invariant functions is a polynomial algebra in the phi i's, phi 1 up to phi n, where n is the rank. And then you can actually prove the following, that if you take any of these, say, multi-indices, so I use this for multi-indices d1 up to dn, then I have a lambda spherical weight. So it's a lambda spherical, is a spherical weight. I write it as in this form. Then actually, oh, I see I made a mistake again. Sorry about this. This should be plus lambda spherical. So if I take any of these matrix valued spherical functions, and I take the corresponding weight from P plus G mu, so which I write as an element from the bottom, plus a spherical weight, then I can wonder, can I simplify this? Can I understand this in terms of this E mu being an algebra over E naught? And actually you can actually write such an element, you can write it as a linear combination of polynomials in the zonal spherical functions that generate the bi-K invariant function, so that's phi 1 up to phi n, times a linear combination of the matrix valued spherical functions corresponding to the bottom. So essentially you can make this association very explicit. And the fact that this is a polynomial of total degree, the length of d, that's exactly where this third assumption goes into. So the first assumption is like multiplicity freeness. The second assumption is about being able to write P plus of G mu as a direct sum of the bottom elements plus the spherical weights. And the third condition, which is this length condition on this spherical weight, that exactly gives you the opportunity to show that this is indeed a polynomial of total degree d. So what I do next is I collect all these polynomials in phi of a, which is an abbreviation of phi 1 up to phi n. So I put them all into a matrix, and the matrix is what I equals j is 1 up to capital N. So in the I and the j are in the labeling of these bottom elements. So that is a polynomial in phi. And I denote the weight, which is also a matrix. And this matrix is just of this type. So it's the trace of the phi mu for a bottom element times the adjoint of another bottom element. Right, so they correspond to mu I and mu j. We saw previously that this function here is actually by k invariant. And you can easily show that it's also a polynomial. And that means that this w is actually a polynomial in phi. So this w is always a polynomial in phi 1 up to phi n. Okay, and then essentially what you do is you write out what the Schur orthogonality relations give you. And then you get a matrix times another matrix times another matrix. And this matrix, each entry you integrate over A, and you use the fact that there is an integration formula over G that reduces to an integration over A. And this is the appropriate Jacobian, which you can write down from Helgeson's book, for instance. And this will actually give you 0 if D is not equal to D prime. And there is an explicit diagonal matrix in case that D equals D prime. So this 0 you have to see as a matrix. So it's a 0, it's the 0 matrix. So that is essentially the orthogonality that you get out of it. And the question is now, can you make this explicit? So let me give an explicit example here. So how do you find these matrix polynomials? How do you find the weight function? How do you find these differential operators? How can you make these matrix polynomials eigenfunctions to a differential operator? And this is in general quite difficult. And what we lack is we lack the control about this embedding. So this k invariant embedding. So it should be k invariant. So this j, that is the k intertwiner, in general is very hard to understand. So we could do this in the group situation for SUN plus 1. This is doable. But if you look for the other case, for the BCN type, then this is kind of difficult. And that's where the work with Jie Liu comes in. In general, you can say something about these embeddings by actually going to bigger spaces. So for this case, you can actually make it very explicit. And in Jie's thesis, there are also results for the case that you replace 2 by, and also this 2 by n again. So there are some, this is a very specific case where you can make stuff really explicit. And I want to explain a little bit in the remaining 10 minutes to show you how you can do this. So what we do is we take this as the group K, and in particular, I can think of U2 sitting inside of K. And what I do is I take U2 and I take its A plus 1 dimensional module, which is A times the first fundamental weight. So I use the standard notation for these fundamental weights for this one. So the fundamental weights of SU n plus 2 are omega 1 up to omega n plus 1. Essentially, this is this one, and this is U2. So you could also easily tensor with a determinant representation, and we did, but I don't want to bring that into the game. I'll show you at the end where it ends up. So actually, what you can show is that then if you take this GK mu, so the A plus 1 dimensional representation of the U2 block, extended as a K representation, then this satisfies all the assumptions. Okay, so this is some work, of course, to do this, but okay, I hope you trust me. And if, in particular, you can make this set of bottom elements B of A times omega 1, you can make this explicit, and it's here. So it's very explicit. It's A minus I times omega 1 plus I times omega 2 plus omega n plus 1. And now we let I run from 0 to A because that is more convenient. Also, it's good to recall there's a result by Kramer. You have two spherical generators, omega 1 plus omega n plus 1 and omega 2 plus omega n. So very explicit. Everything is very explicit. So let me recall that, of course, we take G as UN plus 2, GC is SL M, so it's a complexification. Then this P plus of G is, well, it's behind my own picture, so it's gone. So this is this omega i's. And then we know that the fundamental of the corresponding representation to the fundamental weight omega I is just the ith exterior power of the natural representation of G, which is C to the power n plus 2. And then we know that the highest weight factor is just the wedge product of E1 up to wedge EI. So this is all very explicit. In this case, you can also make this A very explicit. You can actually do this in any case. So I take this linear combination, this matrix. So from now on, AT or AT1, T2 denotes this matrix, which has 2 by 2 blocks here, which are simple cosines and sines, and the identity matrix in the middle. So the identity matrix here is m minus 2 by m minus 2. And then M, the centralizer of A in K, it looks like this. So it has a 2 by 2 block of this type, then some m minus 2, m minus 2 block, and then you get the same matrix, but flipped back again. And this has to be, well, the M has to be in the unitary group of the appropriate size, and it has to be in G, so the determinant has to be 1. And then I think of F1 as this element in the Lie algebra, all the other elements are 0. You can think of it as in the complexification of the Lie algebra of K, which sits inside the Lie algebra of G. So this is the identification that we need to do here. And then instead of looking for this representation very explicitly, what we do is we more or less make it much bigger in order to have some kind of control. And so we look at a much bigger representation. And of course, there's a price to pay. You have to deal with complete, you have to deal with tensor product decompositions. But there's also a gain, namely that you know explicitly what these kind of functions are and how they look like. So essentially, you take this tensor product decomposition, which is relatively simple. This is all true because all the fundamental weights are minuscule weights. So you have a multiplicity-free tensor product decomposition. So you can easily calculate this. And it turns out that some explicit vector V0 is the wedge of E1 and E2, right? Because this one is the second power wedge product. This is the n plus 1 wedge power product. So this is 2 elements. These are n plus 1 elements. So this is in here, and you can actually immediately check that this is a K highest weight factor of the highest weight omega 1. So that corresponds to the fundamental K representation of the U2 block sitting inside K. Instead of looking to irreducible representations, we make it much bigger. So essentially what we take, if I recall that mu I is of this type, A minus I times omega 1. So that's a G representation of highest weight mu I. That's what we're interested in. But in general, this is very hard to write down. So we consider a much bigger tensor product. So this part here, we know for G, that is just the representation in the symmetric power, the A minus I symmetric power of the standard representation. So that's this one. And this one, well, we know omega 2 plus omega n plus 1, that's this one, but we replace it by this tensor product. So we replace this part by this tensor product and we take it I times. So this is a huge representation. It's much too big, but we know that if you decompose it, it will have the highest weight representation mu I sitting in there with multiplicity 1, and then there will be some lower order terms. And now in this one, in this space, we can take this vector u, and this is just the highest weight representation in the symmetric power. And the V0, we know that this is the highest weight representation of omega 1. So the tensor product is also I times omega 1. So what we see is that this one will be a highest weight factor for the K action of weight A times omega 1. So this is a highest weight this is a highest weight factor for the K action for the appropriate weight A times omega 1. So that means that it will generate a K representation of this highest weight type. And we just want to know what are the matrix entries. So we want to know what the matrix entries are. Well, we know that these powers of F1, they generate all the other elements in the representation space, and we want to know the action of such an element AT. And you can explicitly calculate it. I'm going very slow, sorry for this. You can explicitly calculate it. And the nice thing is it's in homogeneous polynomials in cosine t1, cosine t2. So homogeneous of degree, well, you can read it off. It's homogeneous of degree a plus 2i. So you have an explicit embedding, but of course it's a very big space. The advantage is that this space, this function now is completely known. It's completely explicit. It is homogeneous. What we can do, and now, so what we can do is we can actually show that the functions that we are actually looking for are linear combinations of these functions, q and y. So these ones are explicitly known. I should say that these two I've ones which appeared in this slide here, these ones, these are Kraft-tube polynomials, and this is of course not a coincidence. We know that they occur in representations of U2 and SU2. And then we can actually calculate all these coefficients explicitly. We have a lower triangular structure of these functions that we would like to know in terms of functions that we know very well in terms of hypergeometric series, and the coefficients are very explicit. Well, in order to prove this result, you need two key ingredients, namely that the radial part of the Casimir, that you can actually calculate this. And it turns out that it's just a two-term relation. That's why you can solve it, because we know that these are eigenfunctions of this one. And so we have another basis. So we have one basis, that's this base. These are eigenfunctions of the radial part. And this basis, essentially, in this basis, the Casimir operator is triangular. So we can go from one basis to the other, and that gives you this result. Prove this, this is a lot of calculations. Not going to show you anything. And the fact that it is triangular, so the sum goes only up to I, that is due to the fact that if you look at all the lambdas that are smaller than nu I, but still also contained in this space of, if you reduce to k, that it actually contains this representation, it's just all the previous weights of these bottom elements. So that is very neat. So this requires a lot of calculation. It's essential that you know that these q's are functions which are homogeneous, but essentially you can do this. I used a little bit of Maple. Gia did a lot of this stuff by hand. And if you then work out what the orthogonality relations are, so if you then look at the orthogonality relations, then you have matrix orthogonal polynomials, so you have to rescale the variables, sorry for this. And you get matrix valued polynomials. There's an explicit matrix valued weight, which is only depending on this parameter A. And then there's this weight, 1 minus x plus y, 1 plus x plus y to the power b. So here the determinant representation pops in. I took b equals 0. And there's x squared minus 4y, and then you take the square root. And this is 0 as a matrix if d is not equal to d prime. And this is the weight of, this is the region of integration. And this is very well known. This goes back to the 70s. In case of the scalar polynomials, these are Korn-Winners BC2 type polynomials, which were very, so essentially these are Heckman-Opdam polynomials in the case BC2. For specific values of the parameter, we get the general parameters here, but not here. And also these functions are eigenfunctions to a symmetric second order matrix partial differential equation, which is explicit, but still requires some work to do this explicit. So thank you. Oh, let me point out that there's a summer school this summer. It's live in Nijmegen. And I hope to see you, many of you.
Okay, so we'll thank Erik again. Thank you very much, Erik.
Sure.